There are two types of error that could be made when using hypothesis testing. A type 1 error occurs when we believe that there is a genuine effect in our population, when in fact there isn't. Using the conventional criterion that the probability of an error is 0.05 or 5% when there is no effect in the population. Assuming there is no effect in our population, if we replicated the data 100 times, we could expect that on 5 of those 100 occasions, we would obtain a test statistic large enough to make us think that there is a genuine effect in the population, even though there really isn't. A type 2 error occurs when we believe that there is no effect in the population, when in reality there is an effect. This would occur when we obtain a small test statistic, perhaps due to a high variation between our samples. In an ideal world, we want the probability of this error to be very small, because if there is an effect in the population, it is important that we can detect it. The recommended maximum acceptable probability of a type 2 error is 0.2 or 20%. That would mean if we took 100 samples of data from a population in which an effect does exist, we would not be able to detect that effect in 20 out of those 100 samples. Here are some examples of what type 1 and type 2 errors might look like. It might be easier for you to imagine the court example, with type 1 error being convicting someone who was actually innocent, while type 2 error would be not convicting someone who was actually guilty. Here's another example with the alpha level down here, down in the red box. With the alpha level down here, down in indicating a following, falsely saying there is a difference or significance. This can also be referred to as significance, and it's always set at 0.05 for this course. So in this example, if you get a type 1 error, it would mean that the person does not truly have diabetes, but maybe this new test you're running says that they do. The beta value, the type 2 error, is the probability of committing a type 2 error, or falsely saying there is no difference. To fix this, you can increase the sample size. The person doesn't have diabetes in this example, but this new test is, the person does have diabetes, in this example, but the new test doesn't identify them as actually having diabetes. Power depends on a few things. As the sample size increases, power also increases. This is because larger samples are a better approximation in the population. The strictness of deciding an effect is significant, or the significance level, is also a factor in power. If your significance level increases, your power will increase. So in this case, if your significance level is a smaller number, so if your significance level was 0.01 instead of 0.05, that would be considered a larger effect size, or a larger significance level. Variation, which is also the standard deviation squared, in the outcome also has an effect on power. As variation between results decreases, power increases. Conversely, if multiple results have a high variation, the power will decrease. Power is also affected by how big the effect size is. An increased effect size leads to increased power. There are two types of power analysis, post hoc and a priori. Post hoc analysis is when you have already concluded the analysis, and you want to assess the power after the fact. This is not ideal. It does answer the question, did I have enough power to detect a difference if it actually existed? It is often calculated when you did not find a significant mean dependent variable difference between groups, when you expected a difference to occur. Power can be calculated using the number in your sample, effect size, which is calculated by software using the DV, group means, and standard deviations, as well as the alpha value. Here's an example of a G-Power post hoc analysis. G-Power is a free power calculation software application. You can see that in the box off to the top right, there are means and standard deviations for the two groups. This is the mean and standard deviations for the dependent variable. Then you can see in the main screen in the bottom towards the left that the effect size was calculated using those means and SDs. The alpha level of 0.05 was entered, and the number in the samples of both groups were entered. On the bottom right, you can see that the power was calculated to be 0.7249. Since this is less than 0.80, it is not the ideal power we had hoped for, so maybe that's why they didn't get a significant result when they were expecting one. An a priori analysis is done prior to both data collection and analyzing. It answers the question, how many participants are needed in each group to find a statistical difference, if there really is one. So data from previous studies are often used to compute this effect size for a future analysis. Discovered over here. If you wanted a sample size larger, you can see that here you would need a sample size of maybe 210 instead of 160. Here are some resources and software options if you ever find yourself being asked to do a power analysis in the future. G-Power is what I used to produce those few graphs on the previous couple of slides. Analysis software from Vanderbilt, as well as an introduction to power analysis from the University of Connecticut, which goes into more detail than we'll need for this class, as well as a workshop PDF from this workshop that was done in 2008.